Okay, so y equals ab to the x is the general form of your basic exponential function. So when we're using this format, a is, if you're looking graphically or at a table of values, is your y-intercept. And if we're looking at it through the lens of a word problem, this would be our initial value, or where the function starts. B is kind of like the slope of a linear function. This is the rate of either growth or decay. This is what tells you how fast you're increasing or decreasing. So this is our growth or our decay rate, depending on how big it is. Okay. B, you have to be sort of specific. When b is greater than 1, that means that the function is going to be increasing, or that will be an example of exponential growth. If the b value is between 0 and 1, non-inclusive, that would imply a decreasing function, or exponential growth. So b can never be 0, and it can't be negative, because that would really give us a completely different type of function. Okay, so let's look at a few examples. Here are a couple just scenarios or descriptions of an exponential function, and we should be able to put the whole thing together. So in this first example, it says you deposit $500 in an account, so that right there gives you my A value. That's my initial value that this account starts with, and it's accumulating interest at a rate of 2.5% per year. So once we know it's exponential growth, obviously you're gaining money, we build our B value by doing 1 plus whatever that percent is as a decimal. So remember that when we do this, we move our decimal point over 2 spots, so this would be 0.025. Important to remember that when your percent is a single digit, you have to have that 0 in front. So when I write this function out, I get y equals 500 times 1.025 to the x power. So that would be the general form of an equation that you could use to model what's happening with this interest in this account. Okay, so in the second example, we have exponential decay going on. So you're told that a car is purchased for $28,000, and then it's depreciating, which is another way of saying it's losing value, at a rate of 6% per year. So very similar, right off the bat, we know that this is our A value. And since it's depreciating, we're going to take that same sort of model, but this time do 1 minus whatever our percent is as a decimal. Since this is also a single digit, we get that 0.06. So if I write out my function, I get y equals 28,000 times 0.94 to the x. Okay? Okay, so that's writing an exponential function from a description. Now let's take a look at the table of values. So remember, we talked about that A value being not only our initial value in a word problem context, but it's really our y-intercept as well, if we're just looking at the actual numbers. So remember, our y-intercept always occurs when x is 0. So in this case, my A value then is 100. Then if I'm looking at a table, I can do one of two things. I can look at my values and sort of try to figure out the pattern that's happening from one value to the next. I think you can probably tell that these values are being cut in half. And again, we can't write that as division by 2, because in an exponential function, we need to always express it as multiplication. So this is being multiplied by 1/2, or you could say 0.5, over and over again. If you can't tell by looking at it, another really fast way to figure out your B value is to do one value divided by the previous value from the y column or the y row, and that will also give you 0.5 or 1/2. That'll give you your B value. So you don't really have to do anything else. Once you notice that common multiplier, you have your B. So we can put this function together as y equals 100 times 1/2, or you could write 0.5 to the x. Okay, now we'll take a look at a graph. Oh, sorry, just kidding. We'll look at function notation first. Okay, so here's just giving you things in sort of a different way. They say f of 0 is 12 and f of 3 is 40.5. So remember that this is really just giving you pairs of x and y that go together. So this means that when x is 0, y is 12, and when x is 3, y is 40.5. So you could just simply look at it that way, or you could put this into a table. It's really up to you. Basically, we've got the points 0, 12, and 3, 40.5. What's kind of nice about the points they've given you specifically is that this one, when x is 0, that's giving us our y-intercept. So I know that a is 12 in this function. So I don't know b, I don't have the in-between values to figure it out. So the best thing I can do is sort of use my plain old exponential function formula to substitute in what I know and solve for b. So I'm going to go ahead and use the fact that I know a is 12. And I don't know b, but I do have this other pair of x and y. So I'm going to put 40.5 in for y. And I'll leave b as b, and I'll put in 3 for x. So now I'm just really isolating b and then getting rid of that exponent. So at this point, I would divide both sides by 12. If you have your calculator handy, go ahead and punch that in. Okay, so hopefully you got that this gave you 3.375. It's important not to round unless you really have to till the very end, because you want your values to be as precise as possible. So right now, 3.375 is the same as b to the third. So if you remember from class, you can do a couple of things to get rid of this. You could take a cube root on both sides, or you could use the reciprocal exponent. Those two mathematical things would do the same thing to these numbers. So in my calculator now, I'm typing 3.375 caret 1/3, and make sure you put your 1/3 in parentheses. And so I got a nice, pretty nice number of just 1.5 as my b value. So then finally, I'm ready to build my function. This is y equals 12, parentheses 1.5 to the x. So remember, when we write out our function, we're no longer filling in for x or y. Okay, now we'll take a look at a graph. Okay, so kind of similar to what we've been talking about, you're really in some form or another being given a set of x and y values. So I've got these 2 points right here. So notice I don't have my y-intercept. I can't see it on the graph that I've been given. So I'm going to have to do something with these x's and y values. So the easiest thing I can do is go ahead and set up a system of equations. So I'm basically going to fill in my x's and y's in 2 different exponential function formulas. So I would put 1.25 equals, I don't know, a or b to the third. So I'm putting in those values for x and y, and then right underneath it, I'm putting the other x and y values in. Okay. Okay, so like I've done with other systems in the past, I'm allowed to do an operation here to manipulate it. So what I'm going to do is I'm actually going to use division, because when I do that, I actually get to knock out these a's, which is helpful. So I'm going to go ahead and type in 1.25 divided by 0.313. If you get a decimal, which you often will, try to math frac it. It comes out kind of ugly, but I'm going to leave it for now. I get 1250 over 313. And if you remember that when you divide bases like this, you subtract exponents. So this would be b to the -2. Okay, so now we're kind of in the situation we were before. I can use my reciprocal exponent to get b by itself. Okay, so again, I'm just going to go ahead and put that in my calculator. If you're using a TI-83 like the ones we have in class, you put the fraction in parentheses, caret, and then also put the exponent in parentheses. And I'm getting something that really won't math frac very nicely, so I will round it to the 100th for the purpose of this example. Usually you would be told if you were supposed to be rounding. That's okay. For now, we'll just use our b to the 100th place. So I get that b is 1.41. So now the only problem is I still don't know a, so I'm going to have to go back now, use either of these original points to fill in, but I can also now put in b. So I'm going to use the top one because the numbers are a little nicer. So I'm going to do 1.25 equals, I still don't know a, but I can fill in 1.41 for b. And I'll raise this to the third power. So I'm going to go ahead and evaluate 1.41 to the third. Again, I'm keeping it as exact as I can until the end, so I'm going to write out the whole decimal that I got. I have 2.803221. And that's all being multiplied by a. So now I just have to divide to get a by itself. I'm doing this division on both sides. I know this is a little bit annoying to write out. Okay, so in my calculator, I'm doing 1.25 divided by that long decimal. And I'll just stick to rounding to the 100th place since I did that for b, so I get that a is 0.45. Okay, so finally I have all the pieces that I need, so I'm going to go ahead and write this out as y equals 0.45 times 1.41 to the x. Okay, so I have one last example for you. This is an actual word problem that presents you with a bunch of information, and then you have to write an exponential function. So in this case, they're telling us that a population of bacteria is growing exponentially. After 3 hours, there are 100 bacteria. After 8 hours, there are 350 bacteria. So the first thing they want you to do is write an exponential function. They tell you in the format y equals ab to the x. X is hours, that's important, and y is number of bacteria. So that means basically they gave us two ordered pairs. So if I pull the information out of this problem, I really know that 3 is paired with 100 and 8 is paired with 350. So we're going to handle this just like we handled the graph. Again, it didn't say, but I have a feeling if we have to round, let's just stick with the 100 place. So I'm going to set up my system of equations like I did before. So 100 equals AB to the third, and 350 equals AB to the eighth. So same as before, I stack them, I divide in order to get rid of A. So then I'm putting the division of the two numbers in my calculator. I get a decimal, but I'm math fracking it to keep it simple, and I get 2/7, which isn't so bad. And then if I subtract my exponents, I get -5. Okay. So now, like I have been doing, I use the reciprocal exponent to get rid of that other exponent, and I'll have b alone. So these cancel. I'm going to put this in my calculator. Again, make sure you're using parentheses for your exponent. And I do get a pretty nasty number, so I'm going to just round it to the hundredths like we mentioned. So 1.28 is b. Okay, so just like before, now that I have b, I go back and use one of my points. I'll stick with my top one, plug in the x and the y, and also now the b. So 100 equals, we don't know a, b is 1.28, and that's to the third. So again, evaluate 1.28 cubed in your calculator. Doesn't math frac again, so I'm going to keep the whole number. And divide to get a by itself. Okay. Do this in your calculator. And we'll round our final answer to the hundredth. So this gives me 47.68. Okay, so I'm ready to write this function. Y equals the a value I just found, 47.68, times my b value of 1.28 to the x. That's the function that models this bacteria growing over time. If I scroll down here, I do have a follow-up question. It wants to know how many bacteria I expect there to be after half of a day. Okay, well, we need to think about the fact that in this original problem, our x values were in hours, so we need to stick to that. Well, since a full day is 24 hours, this would tell me that I have 12 hours. That's going to be the x value that I plug into my function. So I'm going to write it out. And I'm plugging in that 12 in the exponent spot. And I'm just plugging this in my calculator. So I get a big long decimal. This is bacteria though, which means it's a living thing. I should really stick to the whole number. So I'm rounding it down to 922 bacteria. And that's it. So I've just given you a whole bunch of examples of writing an exponential function. So that should be a pretty good summary.